homework assignment. And then we'll have a final, and the final will resemble the same style and administration technique that we've been using for the homeworks. You'll be doing it online, open book, open notes, work on your own, and it's going to be multiple choice or true-false, and it's going to be comprehensive in that it will encompass many of the questions that we've seen in the past, and you'll have 2 weeks in which to do it, and it will be due really the last day of finals week if memory serves. So I can got my little calendar here. So it's looking to me like the way this semester is wrapping up. Finals week begins on the 30th of April, unless they're going to extend it like the IRS extended its deadlines. That never happens. And then I think our final will be due on the 6th of May, which is the last day of finals week. And so there won't be any extensions on the final. You'll have to get it done in time. And it's not going to be a small final, and I don't know how big it'll be, but it'll be a lot of work, so don't wait till the last minute to do it. But we'll have 2 weeks to do it. And meanwhile, homework 12 is going to be essentially just like homework 11 with a difference, and the difference is we're going to really focus now on doing implication charts and minimization. There's a part of Chapter 9 which has to do with splitting finite state machines into 2 different sections. We're not doing that. There's also, generally speaking, a little bit more overall design work that I like to get done involving Quine-McCluskey, but I'm afraid we're not going to be doing much of that either. So instead what I'll do is I'll focus in on implication charts. We'll have another 8 questions in the in homework 12, and then we're going to focus in on the final and discuss different techniques that we can explore that might help you to review the final. So any questions? Nothing's coming through on the chat, so I guess we got the gang all here, so we'll just get right into it then. Homework 12 leads off with kind of a longish looking finite state machine chart, and I can redraw that chart for you here, and it might be educational for me to do that. So what I'll do, let's see if we can just make it a little bit larger. There. So what I'll do is I'll see if I can draw the chart for you, and then what we'll do is A, B, C, D, E, F, G is in here somewhere, I think. Oh, yep, G. And then, yeah, there's an H over here. And there's even an I right in the center. And if A is a 0, it transitions to I. And if it's a 1, it transitions to C. If B is a 0, it transitions to itself, and otherwise it transitions to I. If C is a 0, transitions to itself, and otherwise it transitions to G. If D is a 0, it transitions to I, and otherwise it transitions to C. If E is a 0, it transitions to D, and otherwise it transitions to itself. If F is a 0, it transitions to I, and otherwise it transitions to C. I guess we can go this way, huh? If G is a 0, it transitions to E. And otherwise it transitions to F. H transitions to itself on 0, and otherwise transitions to A. And you can see H is kind of an orphan. Oops. So that's probably going to get reduced out. Let's label the outputs now. A outputs a 1, H outputs a 1, F outputs a 0, I outputs a 1, B outputs a 1, C outputs a 1, D outputs a 0, G outputs a 0, and E outputs a 0. What kind of machine is this? A Moore machine or a Mealy machine? Any ideas? You can type them on in. Somebody's got their mic open, I think, other than me. Let's see. I'm going to close. Yep. Thank you. You can type in, is it Moore or Mealy? How can I tell? Someone should type something. You can't just sit there like lumps on bumps. Is it synchronous? Well, you tell me. At this point, you should know. Yeah, that's right. It is a Moore machine, and it is synchronous. And the reason we know is because its outputs are only a function of the state we're in, not of the input. If it was a Mealy machine, we might write something like 0, 1 or 0/1. Then that would be a Mealy machine. So this is a Moore machine for sure. Moreover, we can get the present state, next state diagram now. So the present state, and then the next state will be a function of whether x is equal to 0 or x is equal to 1. And then we're going to have an output which is only a function of the present state. And we can tell that because the state is being written in brackets inside of the little state nodes. And so now for the present state, we have to label A through H. And then for the next state, we happen to know that if A is equal to a 0, next state is I. If it's equal to a 1, next state is C. So we write I, C. And then for B, if it's a 0, next state is B. If it's a 1, it's an I. So it's B, I. For C, if it's a 0, we transition to C. Otherwise, if it's a 1, we transition to G. C, G. And if it's D, we transition to I when it's a 0, and C if it's a 1. And then for E, which is over here, if it's a 0, we transition to D, and otherwise we transition to E. And if it's F, if we see a 0, we transition to I, and otherwise we transition to C. And G transitions to E or F. H transitions to H or A. And now for our output, right, we see 1, 1, 1. 0, 0, 0. That's a 0, and H is a 1. And now we've got our present state, next state diagram, and we don't see any obvious row matching, right? Well, here's IC, and there's IC, but the outputs are different. think this says AE, isn't it? E transitions to D. Now it's supposed to be a D. Yeah, no obvious row matching reductions. So now the next step is to use the implication chart. How about B? B doesn't have anything that matches to it. I beg your pardon?
D as in dog.
Oh, D as in dog. D. Oh, yes, quite right. So it looks like there's routine row matching going on here. Let's see if we can get a better pen. D matches with F, so I can get this out. And then everywhere I see F, I can write in D. I guess it's...
I got a question.
Sure.
So I'm kind of lost with the output. How did you get the values for the output, like 1, 1, 0? Like, how did you do that? I'm kind of lost with that.
Yeah, so as it happens, the output here should be coming from here. So if it says A is a 1, then you write a 1 here. If B is a 1, you write a 1 there. If C is a 1, you write a 1 there. D is a 0, so you write a 0 there. So the outputs are in the square brackets.
Okay.
And then now if you want to, you can rerun the row matching and see if there's anything else that we might have missed. So IC, you can't match with that. BI, got nothing. CG, nothing. IC, nothing. DE, nothing. F is out. And now we have ED and HA. So F is gone. A, B, C, D, E. F, I'm going to skip it. G and H. So that reduces our implication chart somewhat. And now we have A, B, C, D, E, skipping F, G, and H. Oh no, we leave off the last letter. Yep. There we go. So now A is different from D, E, and G. B is different from D, E, and G. C is different from D, E, and G. D is different from H. E is different from H. G is different from H. And that's what we have now for the differences in the implication chart. How am I doing so far? Looks like everybody is okay. Let's see if we can't continue. To compare A and B, I have to know if B is equal to I. So I look up B and I.
Okay, I have one more question.
Oh, we left off I. Looks like I is missing. Yes, go ahead.
So for the chart at the bottom, for the left-hand side, how did you get those letters?
The letters here,
Yeah.
these represent the states. So I lettered in ascending order in accordance with the state, and apparently I forgot to include I. So probably I'll show you how you do it. This time I'll do it from scratch. We're supposed to go A through I. For some reason I thought it was A through H. So we start with the second letter, B, C, D, E, F, G, well, I guess we were supposed to skip F, H, and I. I'll just draw a line through it because I'm not going to keep redrawing this thing. And then we have to start from the beginning and go to the penultimate letter. A, B, C, D, E, F, G, H.
Don't we skip F again?
Well, we crossed it out because of the row reduction. If we pretend that we didn't cross it out, it eventually will get removed by the implication chart.
Someone said the sheet is too low. They can't see at the bottom. Thank you.
Thank you. There. So at this point now, we can pretend that F has not been reduced, in which case we can write that A is different from D, E, F, and G. B is different from D, E, F, and G. C is different from D, E, F, and G. D is different from H. E is different from H. F is different from H. G is different from H. And did we forget to put I down here at the bottom here? So I, when I is equal to 0, it transitions to A. And when I is equal to 1, it transitions to C. So it should say A, C. And its output is 1. So now, if you're including, A could be the same as I, but you see D, E. We'll go B could be the same as I. C could be the same as I. D must be different from I. E must be different from I. F must be different from I. G must be different from I. H could be the same as I. We don't know. So this is now, let's get rid of this. This is now the new table, new I'll say implication chart. And now we can say is A equal to B? And the answer is if B is equal to I. We don't know about B and I. So let's look at B and I. Is B equal to I? Oh, well, so if I is equal to C, but we don't know about that either. So let's look at B and I. B is equal to I if B is equal to A. So that's interesting. So we can say it needs BA. B is equal to I if I is equal to C. And this needs IC. Now, if we look at IC, I is equal to C if C is equal to A. And I is equal to C if G is equal to C. Let's look at G and C. It's not. So this is not equal. I is not equal to C because G is not equal to C. And that means B is not equal to I, which means A is not equal to B. And now we can go to the next step. Is A equal to C? If I equals C, it is, but it's not, so that's out 2. Now, is A equal to H? That's the next one. And yes, if I equals H, it is. I could write HI, I suppose. Also, if C equals A. But C does not equal A, so that's no good. We were doing IAH, I think. So this is the one we were supposed to be looking at. That was I equals H and C equals A. Now let's do AI. So that would be A equals I and C equals C. Actually, you know what? A is equivalent to I. Let's put that in a color so we can see it. So now we're back to B and C. B is equal to C if B equals C. That's pretty good. And if I equals G. Well, I does not equal G. And we'll take a look at B and H. B is equivalent to H if B is equivalent to H. And if A is equivalent to I, A is equivalent to I. So B is equivalent to H. So I got another check mark there. And now I can write B is equivalent to H, which is pretty good. Now I got C is equivalent to H if C is equivalent to H, and if A is equivalent to G. A is not equivalent to G, so this is out. Then we got D and E. D is equivalent to E if D is equivalent to I, and it's not. D is equivalent to F if I is equivalent to I and C is equivalent to C. So D is equivalent to F, and there it is. F gets reduced out. And now we have D is equivalent to F. So that was something we had discovered from before when we were doing row matching, but now the implication chart found it for us as well. Now, is D equivalent to G? D is equivalent to G if E is equivalent to I, but it's not, so that gets X'd out. Is E equivalent to F? Well, E is equivalent to F if D is equivalent to I, and it's not. So E is not equivalent to F. Is E equivalent to G? If D is equivalent to E, and it's not, so that gets out. Let's look at F and G. F is equivalent to G if E equals E. Is that an E or an I? That's an I think. Let's see now. We'll go back to F. Yeah, it's an I. Let's go and do it again. F is equivalent to G if E is equivalent to I, and it's not. And H is equivalent to I if H is equivalent to A. No, it isn't. So that goes out. So now,
wouldn't E be equivalent to D?
Is E equivalent to D? So here's DE. E is equivalent to D if D is equivalent to I. D is not equivalent to I, therefore D is not equivalent to E.
Okay.
Right, because I got an X between D and I. So at this point now, everywhere I see an F, I can write a D, which is what row matching was going to do. Everywhere I see an H, I can write a B. I'm not seeing H anywhere else. It was all by itself anyway, so see, because it doesn't really do anything. It's all the way over here. And then A is equivalent to I, so I can take out I, and anywhere I see I can write A. And now it looks like I'm just going to do a quick check to see if there's any row matching, and there isn't. So we are set with a reduced form for this would be homework 12, problem number 1. So my reduced state is going to be how many? 1, 2, 3, 4, 5, got maybe 6 states here. How many are left? 1, 2, 3, 4, 5, 6 states. That's sounding about right. I'm just checking against the answer key, and it is looking pretty good to me. So we are all set. That's our answer right there. What do you think? Any questions about this? Let's see. The sheet is too low. Okay, sorry about that. I don't understand how you can figure out equalities. Could you point at what you're looking at when you're analyzing? Okay. Let's take a couple, like f and d. Right? We know f is equal to d, but how do we know that? Well, we can take f and we look at d, and then we compare, and we say f is equal to d if the outputs are the same, and they are, and if their next states are the same. That is, if I is equal to I, and we know I does equal I, and if C equals C. Well, we know C does equal C. Therefore, D must be equal to F. So it's pretty clear D equals F from that. Does it? You want to try another one, or does it answer your question? So we're looking at next states, and if the next states are equivalent and the outputs are equivalent, then we say the rows are equivalent, and we can do a reduction. We'll do another example if that's all right, unless you have another question about this example. So let's do another one. This is question number 2 in homework 12. It's another sort of fancy looking diagram. And what we can do is I will encode this diagram right here on the next to the diagram, so I don't have to redraw it, because I think it makes things a little bit neater. And so what I'll do is, let's get a fresh piece of paper. Excuse me. And I'll see if I can encode this diagram on the graph paper. So the way I'll do this is I'll write, first of all, is this a Moore machine or a Mealy machine? Moore or Mealy? It's Moore. Yes, that's correct. And we know because the outputs are written here in the brackets. So let's start by writing out the present state, the next state, and then the output. And what we'll do is we'll label these things A, B, C, D, E, F, G, H, and I. And for the next state, we'll have x equals 0 or x equal 1. And then the output, it won't matter whether x is a 0 or a 1 because it's a function only of the present state. How's that? So for A, the next state is going to be A and B. For B, the next state is going to be C and E. For C, next state is going to be F and G. For D, next state is going to be C and A. For E, next state is going to be I and G. For F, next state is going to be H and I. For G, next state is going to be C and F. For H, next states are going to be F and B. And then for I, next states are going to be C and E. Does everybody kind of see how I'm getting that here? Everybody's clear, I hope. No one should be confused by, what I just did. I'm converting this diagram into a table so that I can work with the table. And now for my outputs, A is going to be a 1, B is a 0, C is a 1, D is a 0, E is a 1, F is 1, G is 0, H is 1, I is 0. I think I got that right, didn't I? It's a little bit small here. It's perhaps more clear for me, but if you have this opened on your Blackboard, you can see it as well. It's a little bit larger, perhaps a little clearer. So now I don't need this diagram anymore because the goal is to find a minimized state machine. So let's see if we can do that. Rather than do row reduction, I'm just going to go straight to the implication chart. And we'll start with B. And then we'll start with A and go out to H. Now we've got our lower triangular matrix. We want to compare our outputs. A is going to be different from B, D, G, and I. B is going to be different from C, E, F, and H. C is going to be different from D, G, and I. D is going to be different from E, F, and H. E is going to be different from G and I. F is going to be different from G and I. G is going to be different from H. And H is different from I. So that's a rather sparse matrix of elimination. But that's good. I mean, we got a lot of X's in there, so that's stuff we don't have to consider. Let's take a look at A and C. A is equal to C if A equals F. I don't know about A and F. Let's see if we can figure out A and F. A is equal to F if A is equal to H. I don't know about A and H. And if B is equal to I. Don't know about B and I. Let's look up some of these other ones. Let's see if there's a way in which we can track some of this stuff down. Let's do A and C first. So we need AF and BG. For AF, we need AH and BI. For AF, we need AH and BI. Did I forget AH and BI? I gotta do AE. AE is going to be AI. Oh, AI goes out. So AE is an X. Let's put an X in here. Good. Let's look at AH. A to H needs AF. And A to H needs BB. So if we can get AF depends on AH, and also needs BE. We didn't look at BE yet, did we? Let's take a look at that. So BE has an X in it. So AF needs, oh, that's BI, not BE. AH and BI. BI we don't know about. Let's look at BI. BI is going to be CC, that's good, and EE. So B equals I. So that's good. We've got some reduction in here. B is equal to I. That's pretty good. Let's look at BD. B is equal to D if C equals C, and if A equals E. B equals D if C equals C, and A equals E. A does not equal E, therefore B does not equal D. BD is out. How about B and G? C equals C. Does E equal F? Maybe. So let's put in EF. And now let's go to EF and take a look at it. E equals F if F equals I and if B equals G. Does F equal I? No. So since F does not equal I, E cannot equal H. Right? Because EH requires FI. What about EF? EF needs HI. HI is out, so EF is out. If EF is out, then we can go back to EC. EC says we need FI. FI is out, so therefore this is out. Let's take a look at DI. DI requires C to equal C, that's all right, and A equal E. A does not equal E, therefore this does not equal that. Let's look at DG. DG requires C equals C, which is good, and it requires that A equal F. A equal F. AF, well, let's keep going. CH requires that F equal F, that's good, and that B equals G. So that's BG. Kind of interesting, right? Let's look at BG. BG requires that C equals C, that's good, and that equals F. E equals F. E does not equal F. Since E does not equal F, B does not equal G. Since B does not equal G, H does not equal C. Now let's look at CF. CF is true if F is equal to H. We don't know about that. FH. So C equals F if F equals H and if G equals I. And G equals I. We don't know about G and I. Let's look at GI. C equals C, E equals F. Does E equal F? No. Let's look at FH. That would be true if H equals F and if B equals I. B does equal I, so it does turn out that F is equal to H. And we can put another check in here. That's pretty good. Now let's go back to D and G. D is equal to G if C equals C, and if A equals F. A equals F if A equals H, and if B equals I. A equals H if A equals F and if B equals B. Does A equal F? Maybe. So it's almost as though all of these things are in a cluster. We got FH as a dependence on CF. Let's look at C and F. That's F and H. And G and I. Oh, G and I is out. So this goes out. So CF is out. Now that's good to know. Let's look at DG. DG, it's CC and AF. And AF depends on AH and BE. AH depends on AF. AH depends on AF and BB. And so F and A, it's AH and BI. BI is equal. So I say and we looked at DG, right? So let's do them both. A equals H and F. We got that already. And then what about DG? It's true if A equals F, right? D is equal to G if A equals F. That's right. And we know A equals F. Therefore, D equals G. So we got a lot of reductions here. So the way I would do it, since G can be crossed out, everywhere you see G you can write D. H can be crossed out. F can be crossed out. And everywhere you see F, you can write in A. Everywhere you see H, you can write in A. You can cross out I. And everywhere you see I, you can write in B. And now you've got a nice reduced finite state machine with 1, 2, 3, 4, 5 different rows. Now let's compare that against the answer. Always good to know if you got the right answer after all that work. And 1, 2, 3, 4, 5 rows. A, B, C, D, E. A, B, C, D, E. Yep. A, B, C, E. A, B, C, E. I think we've got a correct answer here. So how about that? That was a good one. These things get complicated, don't they? Any questions about what I've done here so far? How are we doing on time? Well, we have time. So this is about the level of the most complicated finite state machine reduction you're likely to see. And these are the kinds of problems I think you're going to have to work on your own. You know, you can watch me do these things and maybe it'll make you tired, but you won't get the benefit unless you do it yourself. So that's sort of important. So got an important residue here for this homework. And by the way, not to put too fine a point on it, this was homework 12, number 2. And any questions about what I did here so far? I think this was complicated because you had an interrelated cluster of states. They all depended on one another, but that showed their equivalencies. Let's look at the next question. This one is question number 3. And here, it's just like the other questions, only with a difference. And the difference is we now have 2 variables for transition on each state. And the outputs are given as a function only of the state. Is it a Moore machine or a Mealy machine? Anybody want to take a stab at that? Moore or Mealy? Yeah, that is a Moore machine because the output is only a function of the state. If what we did was we said if xy is equal to 0, 0, the output is a 0, and if xy is equal to 0, 1, the output's a 1, then it would be a Mealy machine. But because the output is only a function of the present state, we say it's a Moore machine, and it is synchronous.
Okay, so it doesn't look at it's not determined by the next state.
Yeah, it's determined by the output. If the output is a function of the input, then we have a Mealy machine. I'm going to take this and I'm going to rewrite it here. Let's just move it out of the way because it's there we go. So it's A, C, E, D. D, E, E, A. E, A, F, B. B, C, C, B. And C, D, F, A. And F, B, A, D. And we do the outputs. And they are 0, 0, 1, 0, 1, 1. I think I got that right, didn't I? I'm just checking my work. It looks right to me. If you see any errors, please do chime in, but it looks correct to me. So now let's go in and do the implication chart. I'm giving myself a little bit more space now because I think it'll be a little bit neater if I give myself more space. There. So now we can say that A is equal to B if A equals D. Oh wait, we were going to go and do the outputs and see if outputs are different. So A is different from C, E, and F. B is different from C, E, and F. C is different from D. D is different from E and F. E could be the same as F. We don't know. So that's the output comparison. So it's just like before. Now we do the next state comparisons, and now things are really rather different because we have, well, pretty much a lot of different next states to compare. A will be equivalent to B if A is equivalent to D. Let's do the inverse problem. Are there any things which would compare A and F? Because we know those things are different. And if we don't see anything like that, we could do an AE comparison. Here, A must be different from C because A is not the same as C, but we got that already. All right, let's look at this. AB is different if A is equal to D. We don't know about that. If C is equal to E, we don't know about that. If E equals E, that might be okay. And if A is equal to D, so we don't know about that either. Let's do AD. I'm trying to do some eliminations. If A equals B, if C equals C, if E equals C or C equals E, and if B equals D. Does B equal D? We don't know. Wow, got a lot of different things to compare. Here's B and D. B and D is true if B equals D, and if C equals E, and if A equals B. There's no trivial eliminations here. Let's do C and E. C equals E if E equals C, if A equals D, if F equals F, and if A equals B. And now the next one would be C and F. C and F is true if E equals F, if A equals B, if A equals F. A does not equal F. Since A does not equal F, we know that C does not equal F, which means we can put an X in here. That's pretty good. Now let's take a look at E and F. E equals F if C equals F, and it doesn't. So now let's go back to the beginning. Does A equal B? And yes, if A equals D, if E equals C, and if E equals E and A equals D. And A equals D if A equals B, so it's sort of circularly dependent. AB depends on AD. AD depends on AB, so they're interdependent. Let's go to AD and look again. Also need C to equal C, and it does. We need C to equal E, so it needs CE. And we need for A to equal D, we need B to equal D, and so that's BD. We've got a nice big circular dependency here. All for AD. If all this is true. And now let's look at BD. BD is true if B equals D, and it does. And if C equals E, and if C equals E, and if A equals B, and we already said A equals B if A equals D, if C is equal to E. We don't know about CE. So let's look at CE. C equals E if C equals E, if A equals D, if F equals F, and if A equals B. This needs AB, it needs AD, and it needs AB. We got that already. We have that? CE. So I got C is equal to E if C equals E, if A equals D, if F equals F, and if A equals B. So this is, in my view, a cluster. They're all equal. And so I can say that C is equal to E. I'm going to get a little green pen and do some check marks. I think they're all equal because they're in that cluster. So I got C equals E, I got B equals D, I got A equals D, and I got A equals B already, so that's all right. And so now, if E is equal to C, I can strike out E, and everywhere I see E, I can write C. If I say that D and B are all equal to A, I can strike out D, I can strike out B, and everywhere I see D, I can write A. Everywhere I see B, I can write A. And that's my reduced diagram.
There's a B for C.
Yeah, there's one here. And there's a B over here. And what else? I think that's it. So that's a fairly reduced diagram with only 1, 2, 3 states. That's pretty cool. That's the, yep, and that's an answer. Pretty good. A, C, C, A. And what am I looking at here? A, C, C, A. And it says ACF. ACF. We're there. We're doing it. This says FAAA under F. This says FAAA. And I think we have a good solution here. That's pretty cool. So how about that? A lot of interdependencies going on that caused the cluster to get combined. And we had to go exploring deep into the implication chart in order to find some additional things that we could eliminate. But finally we came back and said, look, there's all these things that interdepend on one another. Therefore, they must all be in equivalence. And that's what gave us our reduction. So, a little complicated, I know. But there you go. This was homework number 12. Problem 3. What did you think of that one? Challenging, right? These aren't necessarily obvious. And you can't do it all with row reduction. It's especially onerous now because you've started to see how complicated finite state machines can get when they have more than one bit. And let's think about this now. If you were to redraw this machine, A, C, F, right, with outputs of 0, 1, 1, then A transitions to A when the input is 0, 0. A transitions to C when the input is 0, 1. A transitions to C when the input is 1, 0. And I'm using this slash to mean or. And A transitions back to A if it's 1, 1. And now I've got C transitions to C if the input is 0, 0. C transitions to A if the input is 0, 1 or 1, 1. C transitions to F if the input is 1, 0. And F transitions to F when the input is 0, 0. And it transitions to A for all the others. So that would be 0, 1, 1, 0, and 1, 1. Complicated, right? Because your transitions are a function of two variables. So the diagram got complicated as a result. Any questions about that? Oh, questions. So this homework was pretty challenging, I think, and it goes on because there's only 8 questions, but the questions are hard, I think. These are the hardest implication charts I ever do. After this, well, after this you can use Quartus to do your finite state machine reductions if you like. Okay, so prepare yourselves. Now that we're doing two variable implication charts, they can get long. Ooh. What do you think of that? That's a good one, right? This might take us more than the remaining time, and we have 28 minutes. No, we have 18 minutes, I think. Well, there's nothing for it. We're gonna have to write it down. And it's A through K. A, B, C, D, E, F, G, H, I, J, K. Present state. Next state. X equals, no, it's XY actually. XY equals 0, 0, 0, 1, 1, 1, 1, 0, 1, 1. A, B, C, D, E. And what does that buy me? I had a bunch of stuff to do here. BICG. Let's see, BCFG. That's a B. HDDF. HCEG. BCIG. FIIK. JKGH. JKGH. EFCG. IIID. BCFG. ACEG. Does that look right to everybody? So let's do the implication chart. We'll start with B, go all the way to K. I'm giving myself a little bit more room now. And now what we're going to do is start with A and go all the way to J. It's hard to get it all in there. Well, not my neatest job. Oh, did we forget the outputs? Oh dear. So there's the outputs. 0, 0, 1, 1. This is a 1, and everything else is 0. So now, compare A to C, D, and K. B compares to C, D, and K. C compares to E, F, G, H, I, and J. Looks like we're missing a... How did that happen? Something's not right with this chart because this row is not right. So B, C, D, E, F, G, H, I, something's not right. I hate to say it, but I may have to redraw this because it's not coming out right. My alignment, I tried to give myself more space, and in the process I messed it up. So I'm just going to redraw it real quick and see if we can't get this right. B, C, D, E, F, G, H, I, J, K. A, B, C, D, E, F, G, H, I, J, and then you stop. So here comes B. C, that's why I like to use graph paper. There. So that's all right. That looks fine. So what we're going to do, I can't fold it. I've got to tear it because otherwise you're going to see through it. Here's the original table. Because I'm backlighting, that's why you have to tear it. So now we want to see what's different. A is different from C, D, and K. B is different from C, D, and K. C is different from E through J. D is different from E through J. E is different from K. F is different from K. G is different from K. H is different from K. I is different from K. And J is different from K. So that makes it a little nicer when you have it in a compact square, even though you don't have much room to write anything. So now we got to do the comparisons. And we got to compare A through B, A to B. So I got B is equal to B. Yep. What about C and I? So here's C. There's I. There's an X, so that gets out. Now let's compare A with E. A is equal to E if B equals B. That's all right. If C equals I, C does not equal I, so A does not equal E. A equals F if B equals F. I don't know about B and F. And then if I equals I, that's all right. If C equals I, and it doesn't, so that's out. A equals G if B equals J. B and J we don't know. If K equals I, and it doesn't, so that goes out. A is equal to H if B is equal to E. B, E, we don't know. A equals H if F is equal to I. F equals I, we don't know. If C equals C, that's all right. And if G equals G. So let's take a look at F and I. F is equal to I if F equals I. That's all right. If I equals I, yes it does. I equals I, yes it does. How about if K and D? So let's look at K and D, we don't know. So F and I all depend on K and D. K and D, let's take a look at that. K and D are true if A equals H. We don't know about A and H. C equals C, E equals E, G equals G. So this K-D thing, it all depends on A and H. And A and H depends on Fi and BE. And Fi depends on KD, and KD depends on AH. That's looking like an awful lot like a circle. Let's keep going. How about A and I? A and I is going to be J and, sorry, that's B and I. B and I, we don't know. A and I depends on I and I, that's all right. C and I. C and I is an X, so this goes out. How about A and J? A and J depends on B and B. C and I. C and I gets an X, so that goes out. How about B and E? And that's about all the time we have on this particular example. So let's put a bookmark on that one, and we'll try and do it again next time. This was problem number 4. Why don't you guys try number 4 and see if you can come up with an answer? I'm working through it, but we don't have time because we are at the end of the class. I hope that was of some help. And someone said, is this still a Moore machine? And the answer is yes, because the output is only a function of the present state. And so that is a Moore machine for sure. So thank you all. Stay safe. And I hope you have a good weekend. Thanks a bunch. Bye-bye.